Thank you. Okay, we're going to continue. I'm going to describe your work for the next week. So, where are you? Okay. Can you read? Can you read?
Yes, doctor.
Okay, so let's start by the last one here. Mr. Ramon, would you please read it? You have? Mr. Ramon? Mr. Ramon, are you there?
Yeah, doctor, I'm here.
Would you please read?
Okay. You have to calculate the roll response of a simple ship model in regular wave.
Okay,
The process.
Okay. Just a second. This work is about regular waves, okay? Roll response. That's the chapter on uncoupled roll motion. So that's exactly what we are going to be doing. Simple. As I said before, section is going to be constant, simple. So there is nothing, there is no dependence in the X direction. Go on.
The process includes to determine the various terms of the equation of motion to find its solutions.
Okay, so this process here, this point here, is just will guide you in the several steps that you have to follow. Okay, go on, please.
Okay, the first, determine the metacentric height Hem of the model, completing a inclining experiment for allowing low-attend conditions.
Okay, Mr. Delgado, do you describe for us, how do you complete an inclining experiment, Mr. Delgado?
Yes, doctor. Okay. We have the variation of the loading condition.
No. Come on. Inclining experiment, Mr. Matute. Inclining experiment, Mr. Matute. You're very close to graduating and still don't know what is the inclining experiment is. Come on, Mr. Delgado. You're telling me you want to stay one more year at university. That's what you're telling me. I don't want to, but you asked me to do it. Yeah, I can give it to you, but Mr. Matute, please listen to me. We can listen to you. Mr. Matute, explain us. In Naval Engineer Matute, explain what an inclining experiment
is.
is.
Experiment is the mood weight.
What? Say that again, please.
Sorry?
Repeat it, because I didn't understand what you said.
Okay, in this experiment is the mood weight on the, okay.
Oh man, we're in trouble here. Miss Freire, tell me. Miss Freire.
Yes, we have to take the distribution of the weights. Then we have the movement of the weights in the model. We have to do the static equilibrium to find.
He looks like a lawyer. You don't look like an engineer, Miss Freire. Miss Vega, Engineer Vega, Naval Engineer Vega, please explain me what an inclining experiment is.
The first is establish the model in the tanks. The second is translate the weight in the port and starboard.
Okay.
and I take the angle
Okay.
for each movement, the weight.
Okay. And then there is a, do you remember, Mr. Jimenez, do you remember the relation that you have to apply in order to get the GM?
Just that we need to calculate or find the buoyancy center, the gravity center.
No, please listen to my question. My question is, do you remember the relation to obtain the GM from an inclining experiment? I don't remember. That's what I'm asking.
The transversal inertia over the volume.
No.
Oh.
GM after an inclining experiment. Mr. Astudillo, do you remember how to determine a GM in an inclining experiment? It's a formula, I think it's WD divided by delta. Is that?
Displacement by the angle recorded.
Yeah. So it's WD divided by the displacement, the tangent of the angle, right? That's GM. Okay. So there you go. So you measure the distance that you move a certain weight value W and register the angle that the system gets. Yes. If you know the weight of the total weight of the model, then you will have a GM. There you go. So if you know the KM, that's easy because you know the hydrostatics, you can determine KG. Okay, let's go to step 2. Who is next? Ms. Lopez, please, step 2.
Apply the formula from Bhattacharya's book to estimate the virtual radius of gyration.
Okay, in more or less, what value would you expect for the virtual radius of gyration, Ms. Lopez? More or less, what value would you expect?
C.
What? What value? What value?
0.55.
Of what?
I don't remember.
Maybe 0.3 by beam.
Exactly, of the beam. In this case, people, this is a very simple model. So this is not a ship. So there is no superstructure. Okay. So probably you're going to attain a value which is below 0.3. Okay. So, okay, don't get scared. Okay. If you got something below 2.3, that's because you don't have superstructure. Okay. Makes sense. Okay. Let's go to the next step. Ms. Guthenberg, please, step 3.
Yes, doctor. Applying Imeno's method to estimate wall damping coefficient.
So for this, I'm going to give you the program, but I'm going to give you a data file as an example. And what you can do is you can take the information and put it in there. So since in this case, the section is uniform, I suggest a good number would be 3. So include 3 sections, constant sections. So internally, you can integrate, or the program can integrate using any integration rule. Okay. If you want to include more, do it, but I don't expect to be much of a difference, right? Because with 3 constant sections, you can do a nice integration. In that case, you have to use Ikeda's formula to estimate the wave damping. Okay, you have to do it. You have to look for the formulation, and that's it. Next step, Ms. Matias, can you talk? Ms. Matias, can we listen to you, Ms. Matias? Or you have problems with the microphone? No? Yes or no? No, okay, Ms. Matias doesn't want to talk. Mr. Barba, step 4.
Yes, estimate the excitation moment with the simplified procedure present in class.
Presented.
Presented in class.
Yes. So this is the formula that we have just obtained. We have the K. For the K, you need the wavelength. For the inertia, we just deduced the formula for that. I think Mr. Jimenez was the one who deduced correctly the formula. So it's LBQ divided by 12. You got a K. For the wave amplitude, you have to record the profile of the wave, get the vertical distance from the crest to the throw. That's the height divided by 2. That will give you the amplitude. Density, fresh water. So you have everything. So you got the weight, GM, inertia, virtual, damping, excitation. Next step, Miss Hidrobo. After you have everything, Miss Hidrobo, go on.
To calculate the amplitude of response in regular wave from product 3 per centimeter of wave count.
Okay, so this way that I want you to present the results, we're going to be discussing that in the next chapter. Okay, that's what we call the RAO, R-A-O, Response Amplitude Operator. Okay, that means that we're getting ready to calculate the response in irregular waves. Okay, so we need this parameter. Okay, so you calculate the amplitude in degrees. You know the excitation since it is a small wave, we express it in centimeters. For example, for these calculations, you can take directly 1 centimeter as the wave amplitude. So directly, what you calculate is the RAO in degrees per centimeter of wave amplitude. Okay, and of course, in that graph, you're going to have an increment in the resonance region and then a reduction in response. Okay, any questions about this? No? Okay, now for the encounter frequency here, for the encounter frequency, what I suggest is that since you are going to be receiving waves from the beam, okay, what you can do is you can, once you have all these parameters, it's easy that you can change the excitation frequency. And the idea is that we plot the response in the region where you have resonance. So you center your excitation frequency at the natural frequency. And you take frequencies a little bit below and a little bit above. So you see an increment and then a reduction. Again, all of this, we're going to check in the second part. Mr. Manrique, how do you feel? How many hours do you think you need to complete this assignment? 4?
No, more.
Okay, 4.5.
Maybe 6 hours, but I
That's all. Good.
maybe.
Okay. So this part has to be solved individually. Now, this Friday, some of you will come and we will do some tests to check this result. Okay? So let's continue. Mr. Manrique, would you please read the objective?
Sure. The objectives: compare the theoretical estimation of the response amplitude operator in role of the simple sheet model with those obtained from experimental tests.
Okay, so you have your individual work, theoretical. Now let's go to the experimental and hopefully they will be close, hopefully. That's the objective. Mr. Zamora, would you please introduction?
Introduction. Present a short explanation of the importance of roll motion calculation in ship design. Then the various sources of uncertainty to fulfill analytical procedures to calculate the roll response of a ship in waves, damping, wave excitation, nonlinear riding arm relation with roll angle, and finally
Please, Mr. Zamora. There is points. There is dot. When you see a dot, that means that you have to complete, you have to finish a sentence. So try to see, let's suppose that nobody is reading this, right? You have to tell the audience that even though they cannot read, they have to transmit that you're finishing a sentence when your voice. Okay, so when you finish a sentence, you have to tell the audience that you're finishing just by the way you pronounce the words. Okay, let's read the last sentence.
Finally, present the objective of this report.
Okay, all of this is the theoretical, the introduction of the report. Why is so important to calculate roll response? What are the difficulties? And that's what we need from time to time. We need experiments. And finally, after all of this, you say, okay, in this report, we are going to, okay, don't write objective to, no, it's just a part of the redaction. Okay, so it's just the last paragraph of this part, the introduction, you say, okay, after all what you have said, you say, okay, in this report, we are going to, if you want to change a little bit the wording, okay, the words in the objective, you can do it. There's no problem. Okay? Questions so far? Questions, people? No question. Good. Okay, let's go to the second part. Let's go again, Miss Pincay. Miss Pincay.
Yes, doctor.
Go on.
Metacentric height. Explain the procedure to determine GM with an inclining experiment.
Okay, just an explain. This is a theoretical roll response. I mean, this is a theoretical part of the report. Just explain. Don't give me too many details because we're all naval engineers and that's all. So for example, how many motions did you take? Things like that. How did you measure the angle? Okay, the procedure. That's all. So this part here will give you the GM value for the theoretical calculations. So, but this is part of the experimental. I mean, there is no way we can just take a value for GM. That's what we need to do the experiment. This Friday, you have to do the experiment. The first thing that you have to do is to weight the model and then do the experiment. Okay? Mr. Zambrano, step 2.
Damping and virtual radius of gyration. Explain the procedure using a free decaying oscillation and applying the concept of logarithmic decrement. Damping coefficient might be calculated.
Okay, so you take the test, the model, incline it, and leave it. So it oscillates, and the oscillation is decaying. So you take the largest value, and with the largest value, you calculate the decremented logarithm. From there, you get z. And also, from the distance from point to point, you can calculate you have the GM, you have the weight. So the only parameter that you need to calculate is the virtual inertia. If you know the damping, which was already calculated. Okay, so from step 2, you get the damping coefficient and also the virtual inertia. Damping coefficient, you can compare it with Jimenez procedure. Virtual inertia, you can divide it by the mass. You can calculate the virtual radius of gyration, which you can compare with the formulation from Bhattacharya. Make sense? Okay. Step 3, who's next? Mr. Delgado, please. Mr. Delgado, step 3.
Response amplitude operator. Explain the formula to estimate the excitation moment from being wave and the procedure to calculate the roll amplitude response.
Okay, so it's basically to explain how to do it. Okay. If you need to include a formula, include it there. Don't include too many details of the formula because there's not much space. Now for the experiment. Who's next? Mr. Matute, please. Experimental development.
Experimental development. Present a short explanation of how the objectives are to be researched. Then describe.
First, please, Mr. Matute, again. Let's suppose that we are not able to read this. You have to tell the audience that you are completing a sentence. Okay, so you said, present a short explanation of how the objectives are to be reached. And you say reached. And everybody understands that the sentence ends there. Go on.
Okay. Then describe the fragment employed and the procedure applied to obtain the required information.
Yes. Okay. So that's what you need to include in there. So it's basically how are you going to reach the objective? What equipment are you going to use? Okay. Don't include, for example, sometimes I use a rule to measure length. Come on. Don't waste time. Who's next? Mr. Galarza, you didn't read the first time. Please, discussion.
Discussion of results. After plotting the theoretical and experimental response amplitude operator, comment on the closeness between them.
Okay, so hopefully they will be close. Hopefully. Or go on.
To try to explain source of discrepancy. Try to explain source of discrepancy.
It is possible that there could be some discrepancies. Okay, let's try to see if we can explain the source of these discrepancies. Okay, that's the idea. Now, for the experimental procedure, okay, we have been working with Giovanna and Andy Miranda this afternoon. And what we're going to do is this. Okay, so you take the model, okay, put it to float, put some weights until you're setting up a loading condition. You take the model, weight it, or we can wait at the end, okay? And the first thing that you have to do, according to is to determine the GM with an inclining experiment, okay? You can do it. Hopefully you approve stability course. One thing. Then you incline it and let it roll. So you record the oscillation, which is decaying. Not once, not twice, at least 3 times. Check that the register is adequate. You have good information from there. That's the second part. Now, with this record, you see the distance between crests in time. That's period. You get the inverse, that's frequency. And now, what we want to do is to excite the model with waves, okay? In the range of frequency, which includes the natural frequency. Of course, we want to observe resonance, of course. So let's suppose that the natural frequency is 1.5. Let's suppose 1.5. Okay, so what we can do is we can take 3 frequencies below 1.5 and 3 frequencies above 1.5, at least. And of course, we need to do the 1.5. So, and that Giovanna will help you. So let's suppose that it's 1.5. So what we can do is we can take, for example, 0.5 below, so 1. Well, maybe that's too low. Okay, let's 0.4 below, 0.4 below, and 0.4 below. And then we go 0.4 above, 0.4 above, and 0.4 above. So you have 7 frequencies with the center at the natural frequency. So in that case, the generation of the waves will be with constant frequency for 2 minutes. And you will be registering the oscillation of the motor. With the register, you can determine the amplitude of the roll motion. The waves are being generated. Unfortunately, we do not have the device to measure the elevation of the water. So what we have to do is you can record the profile. That's something that you did some weeks ago. And from there, since the wave is, the frequency is constant, you can measure the distance between crests, that will be lambda, and you're gonna measure the distance from the crest to the throw. That's gonna be the height. Divided by 2, that's your amplitude. So you have GM, damping, virtual inertia, wave characteristics. So you can do all of this to calculate theoretically. And you determine experimentally. And then compare. Questions? Everything is crystal clear, or everything is just a mess? Mr. Barba, do you have any question?
No, doctor. No,
everything is clear.
Yeah, so.
How many hours do you think it will take to complete this report?
The report in 1 week is good.
Okay, so it's about 10 hours. Good.
Yeah.
Remember that you are 3 people, not 1, not 2, 3 people. So if you organize correctly, I mean, if you say it's 10, 12 hours, that's probably it's about 4 or 5 hours per person. That's all. That's not much. Okay. So you see, for example, you have the GM, you have this, you have that, the excitation. So, okay, you do this, you do that, you do that. Everybody does that. And then we get together, get every parameter, Excel table, bang, and that's it. But you have to work as a group, as a team. People, is there any questions about this? Any questions about this? No questions? Okay, before we break, let me give you some warnings, okay? This Thursday, we're going to start chapter 5, okay? So I want you to start reading chapter 5. Chapter 5 implies that we have to start facing not deterministic, okay, but random processes. Because you have been at the beach, right? And you see that the waves are not regular. So we have to face that. So we're going to start these studies this Thursday. Okay, now, since on Friday, we're going to do some activities here, next Tuesday, we're not going to have class. Okay, I will be available at night if you have questions about the homework. Okay, then on Friday 28th, Thursday 28th, we're going to have a session about how to use MaxSurf, the module, what's the name of the module? Motion. The motion module of MaxSurf. Okay. So it's a good idea if you have available your projects from MaxSurf close to you. So Giovanna is going to explain that. If you have questions, will be a good point for you to ask Giovanna, because that's the program that you need to use in the final project. Okay. Then on Tuesday the 2nd, I'm going to continue with the material. And then on Thursday 4th, we're going to have the next evaluation, because that's the 4th week. Okay. Then on the next day, Friday, we're going to do tests in the towing tank and in the wave tank again. We're going to do something similar. We're going to place the model in the tank, and we're going to apply waves, but the waves are going to be irregular. So it's going to be nice. We're going to see the waves are not going to be like that. It's going to be like that. So what we're going to register is the angle, and we're going to calculate what we call an spectrum of the response. So we have the response of the excitation, we have the response of the ta-ta-ta. So we're going to see if we can calculate the response of the spectrum of the response using the RAW and the response of the excitation. Okay. And after that, we have 3 more weeks. That's basically pushing for the project. Okay. So we're going to explain some, but mostly we're going to keep track of your projects. Any questions about this itinerary, this schedule for the next 4 or 5 weeks? No? Okay, I'm going to post it tonight, the assignment. Okay, and on this Thursday, I'm going to check how far have you come in the calculations. We are tight, so we have to start right away. Okay, people. See you Thursday. And hopefully on Friday, everything will be ready for you on the lab. If there are no more questions, then I'll see you Thursday. Bye-bye now.